Every second of the day, 250,000 text messages, 60,000 Google searches, and 9,000 photos are shared around the world. Storage technology is constantly trying to keep up with demand. Since the 1950s, improvements to technology have increased storage density a billionfold. The development of the internet was made possible thanks to these advancements. Today, our hard drive servers and data centers face the same problem: how to save more information on smaller surfaces. The Jean Lamour Institute in the east of France is home to researchers imagining the materials of tomorrow thanks to a very unique setup. To get a closer look, one must wear a special suit to keep from contaminating the air with dust. Danielle Pierre helped create this platform, christened Dome, a 70-meter-long tube on which 28 high-precision instruments have been mounted. Their vacuum-sealed conditions enable the creation of new materials at the atomic level. Scientists use common atoms like iron, cobalt, or nickel, but assemble them in order to produce new properties. These materials can improve solar panels or increase the performance of tomorrow's magnetic memory.
We'll move sample materials through this transfer tunnel. We place a base layer in these containers. Then we deposit the sample we want to study later in various machines. So we'll be able to create what will be hybrid materials using a variety of different depositing techniques. We'll be able to study them, define their characteristics, see their structure. We do all of this under ultra-high vacuum conditions.
Today, in order to miniaturize and increase the storage capacity of magnetic materials, scientists are looking to code at the level of electrons. But the speed of writing and reading this information is up against the limitations of today's mechanical elements. Physicists have conceptualized powerful lasers fast enough to code and decode our data on magnetic material. This could also reduce energy needs for our ever-multiplying servers.
We're trying to store more and more information in ever smaller spaces, and we want to do it faster. It's an evolution that's taken place over 20 or 30 years, but what's become a bigger concern is the effect of our energy use on global warming. Sending an email, watching a video uses energy. Today, the internet makes up 5% of global energy consumption. As we develop the Internet of Things, we'll generate an absolutely enormous quantity of information. So we need to increase storage speed while reducing its physical size and energy use.
To test the efficiency of these magnetic nanomaterials, scientists must send samples to their collaborators in the outskirts of Paris. The C2N, a nanotechnology research center, has the cutting-edge tools to work with these new materials. They're collected here in one of the largest clean rooms in Europe. These machines can manipulate the materials on a level 1,000 times finer than a human hair. The scientists will be able to observe the material's stability, which needs to store information for a minimum of 10 years.
The first step is to characterize the materials we receive at the level of their magnetic and electrical properties. After we've done that, we move on to the nanofabrication, which has multiple stages. We have a form design stage from which we enter the stage of applying that form to the material. From there, we move on to the testing stages in the clean room, where we proceed with manufacturing. Then we'll test its magnetic and electrical properties again. Ultimately, it won't maintain the same properties that we originally received from the team of the Jean Lamour Institute.
While this research revolves around fundamental science, its application is already being considered by a number of industries struggling to handle our growing data production. Today's zeros and ones will grow exponentially, with the evolution of robotics and automated cars steadily becoming an environmental problem. Since you started watching this film, over 9 billion gigabytes of information were produced globally.